This is Burj Khalifa, the current tallest skyscraper in the world, rising to a height of 828 meters, beating the previous holder, Taipei 101 in 2010, by a large margin. Yet the next in line to become the tallest building in the world is the Jeddah Tower, currently under construction and is designed to a height of at least 1,000 meters. While this seems impressive, there have been many proposals for mega tall skyscrapers, rising to 1 mile and some even higher. So how feasible are these mega tall skyscrapers? Engineering, construction and maintenance of mega tall skyscrapers is so complicated that they are often overlooked when discussing this topic. The fact is, higher doesn't always mean better, and in this video we'll explore the engineering and economics behind some famous mega tall skyscrapers to find out how high we can build. Let's dive in. It is no surprise that the need for cities with tall buildings boiled down to overpopulation and efficiency. As the world population will drastically increase in the future, cities have been growing to keep up with this demand to provide both living and work opportunities. This migration of the rural population to cities is a major cause of this increase. Once people get used to urban living, they rarely go back to the countryside. Only 30% of the world's population was urban in 1950. Today, 55% of the world's population resides in urban areas, and it is estimated that the urban population will further increase to about 70% by 2050, according to the United Nations Department of Economic and Social Affairs. To prevent urban sprawl and the destruction of valuable agricultural lands and improve transport, cities have been growing vertically rather than laterally. The humble beginnings of the first multi-story building were only made practical through the use of elevators and steel. In 1857, the Howard Department Store in New York witnessed the installation of the world's first passenger elevator, invented by the American industrialist Elijah Otis, and could travel 5 floors in less than a minute. Yet the earliest skyscraper rested on extremely thick masonry walls at the ground level, which limited how high we could build before building collapsed on its own weight. Architects and engineers soon turned to a cast iron, a wrought iron framework, to support the weight of the building upper floors, allowing for more floor space. It was, however, the refinement of the Bessemer process in 1860 that allowed for a major advance in skyscraper construction. This inexpensive industrial process allowed for a major mass production of steel from iron. As the steel is stronger and lighter in weight than iron, the use of steel frame was possible in the construction of a truly tall buildings. The home insurance building in 1885 in Chicago was what most considered the world's first skyscraper. Not only passenger elevators were used, but also an early version of a steel skeletal structure was used for the first time to bear the weight of the building exterior walls. This innovation was accredited to William LeBaron Jenney, who is also widely recognized as the father of American skyscraper. His work made the modern skyscraper possible. The metal frame design was relatively fire resistant compared to mostly wooden central city of Chicago. The home insurance building didn't have to get thicker, darker and heavier to get taller, unlike its predecessors that were supported by nothing but their own masonry walls. Its steel frame structure weighted only third as much and proved that high-rise buildings could be a solution for density problems, and with those two essential technologies, a new building type was developed rapidly. And with that, the skyscraper height race began. Let's do this quickly. Starting from Park Row building in New York that reached 30 stories in 1899, using the same steel frame system. Soon after, many skyscrapers were constructed in New York in the following years, getting higher and higher. The threshold height of 300 meters was first reached by the Chrysler Building in 1930. This was overtaken by a 381 Empire State Building. Although this was a breaking record building, there were virtually no open spaces on all floors of the building. Just have a look at the building's 61st floor. Steel columns and beams formed a stable 3D grid throughout the entire structure. However, such closely spaced columns obstruct open spaces in the building. World Trade Center followed the same steel frame structure as the Empire State Building in 1973. The Sears Tower or the Willis Tower moves away from the structural frame of its predecessors to a revolutionary bundle tube structural system, which is a cluster of 9 tubes connected together to act as a single unit. The tubes support one another and strengthen the entire structure. Toward the end of the 20th century, the region with the most tall buildings shifted from the US to Asian countries. The title for the tallest in the world was taken by the Petronas Towers in 1998 in Kuala Lumpur. The 452-meter towers exceeded the architectural height of the Willis Tower, which still held the title for the tallest occupied floor building by then. In 2004, the 508 Taipei 101 in Taiwan finally eclipsed both architectural and occupied heights of the Willis Tower and used a new structural system known as the core outrigger. On some levels, the inner core is connected with the parameter core for more stiffness. And if this starts to become confusing, don't worry, we'll get into this later in this video. In the 21st century, the Middle East also jumped in the skyscraper race with the 828 tall Burj Khalifa, which took the title for the tallest building in the world in 2010. However, Burj Khalifa will soon lose its title to the Jeddah Tower, which has been under construction for quite a while now, but that's a discussion for another video. The building is expected to reach a height of over 1 kilometer in Saudi Arabia and will finally surpass the Burj Khalifa. There have also been many proposals for mega tall skyscrapers, with some expected to exceed 1 mile, including this building, which we will get into later in this video, and some reaching even more ridiculous heights like the Exceed 4000. Although this structure was never meant to be constructed, it's a testament of a human ambition. When it comes to building mega tall skyscrapers, the question is not whether these proposals are possible or not. In many cases, it's not an engineering issue. The issue is, why would anyone want to build these structures in the first place? One of the most fundamental architectural challenges is to provide occupiable spaces for people, which many current tall skyscrapers fail miserably in delivering. When the Petronas Towers were completed, it was architecturally taller than the Willis Tower by 10 meters, but the Willis Tower occupied height was 38 meters higher than the Petronas Towers. The height of the Petronas Towers were accomplished by constructing the spires as an integral part of the main structure. The architectural height does not include functional and technical equipment that can be removed, so things such as antennas and signage are not considered part of the architectural height, which is why the Petronas Towers were architecturally higher. Architectural and occupied height differences become even larger as buildings become taller, as owners wish to extend the height of their buildings with so-called vanity heights by constructing spires. The current tallest, Burj Khalifa, with its height of 828 meters, exceed Taipei 101 by a significant margin of 320 meters. However, the occupied height differences between Burj Khalifa and Taipei 101 is only 147 meters. It is also expected that the occupied height is only 80 meters between Burj Khalifa and the Jeddah Tower. Much of this massive skyscraper will be completely deserted. The Burj Khalifa has more than 200 floors, but only 160 of them are accessible to the public. The building 200 floors is so thin that no one can live in it. An excellent example of maximizing occupiable spaces is the Shanghai Tower, which opened in 2015, and it's a 128-story building with an architectural height of 632 meters. While it is still significantly less than the Burj Khalifa, its occupied height is only 2 meters different. Unfortunately, in this era of architectural design, many recent super tall heights are often more monumental than practical compared to those of the 1970s. Tall buildings are used to show off the country's prestige. Yet for a tall building to be considered a skyscraper, at least 50% of its height must be occupiable, according to the Council on Tall Buildings and Urban Habitat. Therefore, you can now build a tower that reaches 2 kilometers into the sky and call it the tallest building. Telecommunication and observation towers do not meet the 50% threshold and are not considered skyscrapers. But is there a way when we can build more functional tall buildings that reaches 1 mile height and have more usable space than current structures? The greatest engineering challenges in tall buildings is to contain the forces of gravity and wind. Tall buildings will likely collapse under their own weight unless they taper off to the top. As the building gets taller, the slenderness height-to-width ratio increases, and the tower becomes dramatically extra sensitive to wind. As a result, it cannot be comfortably inhabited. It is also worth mentioning that humans are surprisingly sensitive to vibration, to the extent that building motions may feel uncomfortable, even if they are small. To overcome the slenderness effect, we can make the building wider at the base, or connect several towers with the bridges at different levels, so they will enforce and stiffen each other. However, it is not always possible when dealing with dense cities with small blocks of land. Structurally, a skyscraper consists of a substructure or a foundation of different types depending on the ground and soil condition, and a superstructure of columns and girders above the ground. We can simplify this by imagining this tall building as a vertical cantilever out of the ground. As we all know, a steel beam consists of two flanges and a web that is capable of supporting its own weight. It is also able to support lateral forces from the wind. Let's see what happens. As the wind blows directly on the cantilever can deflect, and the flanges facing the wind experience tension, while the far flanges experience compression. Yet altogether, a system with its foundation and superstructure can contain both vertical and lateral loads. Just like a cantilever, buildings have structural systems to support their own weight and any lateral movement caused by wind and earthquakes, which are the governing designs of high-rise buildings. Up to 10 stories, the wind loads rarely affect the design. However, for tall buildings, wind and gusting effects become especially problematic. Transverse loading, called vortex shedding, becomes in sync with the building. This effect of wind can be minimized by installing tuned mass damper systems, which reduces the effect of wind forces. We can also aerodynamically shape the building. For example, the Shanghai World Financial Center has an opening that reduces the stresses of wind pressures on the tower. Rounding the building can also reduce the wind stresses on the building. The Burj Khalifa's asymmetrical design isn't just for aesthetic, it's a strategic feature to combat vortex shedding. Wind vortices can never coalesce because the wind encounters a different building shape at each tier. This confuses the wind and eliminates potential dangerous resonance. Therefore, the higher the building, the higher the vertical and lateral loads, and to combat those loads, the building needs more than just a clever external design. It needs an internal structural system that can support itself and withstand lateral loads. There are many structural systems for skyscrapers that are constantly improving with every new building. The tube-in-tube systems are probably the most common for buildings between 40 to 100 stories. The building consists of an inner tube that houses the building services such as elevator shaft and stairs and carries some of the building's vertical loads. The outer tube or the perimeter tube not only carries some of the building's weight, but also resists the building lateral forces. The tube-in-tube system can be further improved by connecting the inner core with the outer core. This gives the building the required stiffness to counteract the lateral loads of the building by transferring those loads to the core of the building through the outriggers. When the building is loaded laterally, the columns facing the wind experience tension, while the far columns experience compression, which makes them more efficient than structural cores without outriggers. At present, the tallest building structured with a core outrigger system is the 632 meter tall Shanghai Tower. However, the efficiency of the core outrigger system cannot exceed some of the most efficient megatube structures, such as the brace megatubes, which uses a fast-spaced exterior columns braced by diagonal members, which transfer gravity loads and vertical loads to the mega columns. An example would be the John Hancock Center. In this 100 stories tall skyscraper in Chicago, you can clearly see the diagonal members which supports the megatubes. This design uses far less steel than the outrigger trigger system. Yet the core trigger system is used more frequently in tall buildings because it's architecturally more flexible in terms of facade design. All the required lateral stiffness of the brace tubes are allocated at the parameter tubes, while the core structure is designed to carry only gravity loads. This means that the parameter columns, especially the corner columns, are quite big, which restrict viewing. These are usually prime real estate locations reserved for luxury apartments and office space. The diagonal trusses also restrict viewing, which is why the core triggers is the preferable design. Yet sometimes the core trigger can be combined with the mega tube system, which result in a mixed system that can reach up to 700 meters. A good example is the Shanghai World Financial Center. During its construction, before all the glass and the building finishes installed, you can clearly see the mega columns of the building connected to the building outrigger and the diagonal trusses. While this looks impressive, the tallest building in the world took a different approach for a very good reason. As discussed earlier in this video, for buildings to get taller, they need to get wider. So if we scale a square building to get 1 kilometer high, the interior spaces become uncomfortable for users, especially due to the lack of natural daylight. Burj Khalifa and the Jeddah Tower moves away from the square building design to a buttress core system. This design not only provides good viewing, but is also structurally much more favorable to use because it's able to confuse wind with its unsymmetrical design. Burj Khalifa has 3 wings that get smaller as the building gets higher. The central core itself is further extended as shear walls into the architectural spaces of the 3 wings and terminated with a thickened wall. These thickened end walls are quite similar to the flanges of a vertical cantilever. The difference is it has a Y-shaped cross section where the extended shear walls act as webs. The wings is also stiffened by additional shear walls called fin walls, which also act architecturally as interior walls. The buttress core system gives Burj Khalifa the stiffness required to counteract any lateral loads, and the building is able to carry its vertical loads by tapering to the top, which means less usable spaces as the building gets higher, and this provides an architectural limitation. But is it possible to build higher without sacrificing much usable space? The answer is yes. Perhaps one of the most radical proposals for mile-high skyscrapers is the superframe conjoined tower design. Fazlur Rahman Khan, who engineered the John Hancock Center, envisioned a conjoined tower with 4 braced megatubes that is interconnected by multi-story trusses. The height of these towers can be increased very efficiently by structurally connecting them. The horizontal braced tubes is what create the superframe, which is basically combining these towers into one building, and uses the width of the entire complex as structural depth instead of the width of the individual towers, resulting in a stiff structure with a huge lateral resisting capacity. This concept can also be applied to 3 buildings in a triangle shape with 120 degrees between them, or even conjoined towers with more than 4 buildings, which is similar to the concept of the Tokyo Sky Mile Tower, or even the Exceed 4000, which is a group of buildings connected together. Despite its characteristics for extremely tall buildings, the superframe conjoined tower design may not be easily employed for existing dense urban land because of the very large building sites required for them. The standard block in Manhattan is about 274 by 80 meters, which means in order to build a conjoined tower with 4 buildings, almost 4 blocks of land will need to be used to make this happen. Considering the limited land size, it would take decades to acquire the lands needed to build such a structure, that if someone has the guts to take on such a massive risk. Although structurally it might seem possible to build 1-mile-high sky buildings, which is an excellent way to prevent urban sprawl, realistically, is building super tall economical? Hong Kong share many similarities with New York. Both are land-starved and surrounded by water. Both are international trade and commerce hub, and both have large populations, with the skyscrapers crowding those 2 cities. Yet the Chinese government decided to ban skyscrapers over 500 meters because of safety reasons and waste of resources. For example, previous projects such as the Shanghai Tower were unable to generate revenue successfully. The project experienced significant cost overruns and delays. The building's total cost was reported to be 2.4 billion, much more than initially planned due to the complexities of its design and construction. The building suffered from many issues such as an oversupply of office space in the city, the rising cost, and the change of work trends that left the building largely unoccupied for many years. Tall buildings obviously cost a staggering amount of money. Burj Khalifa cost 1.5 billion, and the Jeddah Tower reported would cost 1.2 billion. However, it would not be surprising if this figure doubles in the years to come, and any government or entity that pays that kind of money need to recoup the cost somehow, making these builds financially unfeasible. But such projects end up as symbols of the city, which is why some countries justify the construction of such mega projects. In addition to the cost, there are other issues that face tall buildings. The construction of skyscrapers involve intensive use of materials like steel, concrete, and glass, which have high carbon footprints. Due to the energy-intensive processes involved in their production, tall buildings require a significant amount of energy for heating, cooling, and lighting, and operating elevators. According to the UCL's Energy Institute, tall skyscrapers account for 40% of the total energy consumption each year. The main reason is related to heating and cooling. Large windows may provide magnificent views, but they are not good insulators. Even triple glazed windows lose far more heat than a well-insulated brick wall. Supply of water is another issue. Since water does not flow uphill, high-rise buildings depend on pumps to lift water to the upper floors. Tall buildings can have up to 3 different pump systems for chilled water, heated water, and sprinkler system, which require energy and space to function. And let's not forget waste disposal, which is another complicated system that need to be fitted for a building to be functional. Yet the two biggest limitations of skyscrapers have always been fire and vertical transport. It is much more difficult to design fire safety plans for skyscrapers because it takes longer to evacuate during an emergency. Due to the immense height, conventional firefighting techniques are useless. The average firehouse can spray up to 15 meters, which means for a 100-meter tall building this would not work. And in the case of the Burj Khalifa, it's over 800 meters. In such cases, skyscrapers need to be designed so that fire outbreaks can burn themselves out without external intervention and allow people to exit the building safely. This means that skyscrapers need to be constructed using fire-resistant materials so they won't collapse easily. They also need to be separated into compartments to prevent the spreading of fire and equipped with fire suppression systems such as sprinklers to put these fires out. On another issue, the taller the skyscraper, the more elevators it requires. A single elevator cannot get to the top of an enormous skyscraper because the weight of the elevator cables becomes so much for the winch motor to haul. Instead, mega-tall skyscrapers rely on transfer elevators and sky lobbies. The more elevators the building has, the less space there is for offices and apartments. Plus, people would have to wait longer time for an elevator, which is a very difficult issue to balance when working with limited spaces. This is a huge area of skyscraper design and construction that is usually overlooked when discussing how high we can build. Research shows that economic heights for most tall buildings ranges between 40 to 50 stories, which is between 120 to 175 meters. Within this range, tall buildings are most energy efficient and can be built in a minimum time schedule. Densely built low-rise buildings are more space and carbon efficient compared to high-rise buildings with higher carbon impact. Yet unfortunately, the height of tall buildings is dictated by market-driven real estate, ego-driven prestige, and a sense of competition. So in the end, how tall could a skyscraper be? In theory, there is no real limit as long as the base can expand to accommodate the building height and deep pockets to make such a building a reality.